This video we're gonna go through the homework solution for homework 8. So let's look at the first problem 6.23. Determine the force in x and y directions needed to hold this fixed wing, which turn the oil jet in a horizontal plane. So we are given the V1, which is equals to 29 meter per second, and V2 equals to 33 meter per second, and the density of the oil is 0.9 density of the water. So it will give us 0.9 times 1000 kilo per cubic meter. So that will be 900 kilogram per cubic meter. Okay, that's our basic informations. So for this problem, we're gonna draw the control volume as shown in the left, and we're gonna have a velocity come in to the control volume like this, V1. Notice for V1 we only have the velocity in x direction, but for V2, which is coming out here, we will have both the x direction and V2y, which is in the y direction. Okay, so we are given the degree, the angle here, which is 30 degrees Celsius. So for V2x, it will equals to V2 times cosine 30 degree, and the V2y will equals to V2 sine 30 degree. Okay. And we are asking to find the force in x and the y direction. So we will have Fy and Fx, and that will give us F here. Okay. So first we're gonna apply the momentum equation in x direction. So Fx will equals to the mass flux times flowing out times the velocity minus the mass flux flowing in times the velocity coming in here. So the m mass flux is equals mass flux moving and moving out are equal, so they are both equals to rho times q, which is 900 kilogram per cubic meter times the q, which is given 0.9 cubic meter per second. So this will be 810 kilogram per second. Okay. So now we have most of the parameters of the momentum equation. Now we can simplify the equation by m dot times the velocity moving out, which is the v2x, and it's coming to the left, so it's negative minus 2x and minus v1 with v1x, which is equals to v1. Okay. So this will equals to 1 kilogram per second times negative v2, which is given 33 meter per second times cosine 30 degree minus 29 meter per second. Okay, so our fx will equals to negative 46.6 kilonewton, and therefore direction is to the left. Okay, now we're gonna find the momentum, the force in the y direction. We're gonna apply the momentum equation in y direction. So sum of force in y direction equals to same thing, m dot times v minus m dot moving in and the velocity moving out, moving in here, and the m dot is the same thing. So we can simplify the equation. Fy equals to m dot times negative v2y and minus 0, because v1 doesn't have any projected velocity in y direction, so it's 0 here. So Fy equals to 110 kilo per second minus 33 meter per second times sine 30 degree, which Fy is equals to negative 13.4 kilonewton. Now let's look at problem 6.25. We have a water jet here with a velocity 60 feet per second, and we are asking to find the x and the y component of force per unit width needed to hold the vine stationary. So as the picture show here, we have a control volume, and we will have the V1 coming to the control volume, the V2, V3 leaving from it. And because it's free jet, so V1 actually equals to V2 equals to V3 equals to V, which is 40 feet per second. Okay. and V2x, which is equals to V2 times cosine 60 degree, which is equals to V times cosine 60 degree, and V2y equals to similar thing, V times sine 60 degree. Similarly, we can find V3x equals to V times cosine 30 degree. V3y equals to V times sine 60 degree. Okay. Because of the continuity equation, we'll have Q1 equals to Q2 plus Q3. And if we expand that, we'll have V1 times A1 equals to V2 times A2 plus V3 times A3, because we know V1 equals to V2 equals to V3, so we can simplify the equation by V times A1 will equals to W1 times B1 equals to V times W2 times B2 plus V times W3 times B3. Because the entire problem is asking us to find the force per unit width, we'll assume the width is constant. So B1 equals to B2 equals to B3. Okay. So therefore we can get W1 equals to W2 plus W3. And W1 will equals to W2, which is given 0.2 feet. W3 is 0.1 feet. So the W1 is 0.3 feet. So next step, we're gonna find the mass flux M1 here. M1 dot equals to rho times Q1, okay, which will be rho times V1 A1, and therefore it will be rho times V times W1 times B, and the mass flux 0.2 is rho times Q2, and it will be rho V 2 times V. And similarly for M.3, it's equals to rho times Q3, which will equals to rho V 3 times B. Okay. So with the information here, now we can use the momentum equation, which will equals to Fx equals to sum of the mass flux moving out times the velocity moving out minus the mass flux moving in times the velocity moving in. And we are asking to find the Fx per unit width, so the equation actually is something like that. Because we divided by in the left, so by b in the left, so we also need to divide it by b to the write it as well. So 1 over B times the mass flux moving out, which is the velocity of V2 and V3. So dot 2 times V2x plus the m dot 3 V3x and minus the mass flux moving in, which is the m1 dot times v1. Okay. So fx over b will be equals to 1 over b times m dot 2, which is rho v 2 times b plus v2x is calculated here, which is v times cosine 60. So it's v times cosine 60. And similarly for the point 3, rho times v times w3 times b, also times the sine, sorry, it's also cosine 30 degree, and minus rho v w3 w1 times b times v. Okay, so now we can move all the same terms outside. X over b will equals to rho v times rho v squared times w2 times cosine 60 plus w3 times cosine 30 degree minus w1. Okay. Therefore, fx over b equals to 1.94 slug per cubic feet times the velocity, which is 40 feet per second, to the power of 2. And W2 is 0.2 feet. W3 is 0.1 feet. W1, which is calculated 0.3 feet. Therefore, fx or b equals to 890 lbf per feet. And the direction of that will be negative. So it's actually this direction. Okay. We will do the similar thing for the momentum equation on y direction. So the equals to the max flowing out minus the mass flowing in. We will do the similar thing as in the x direction. Fy over b equals to rho v squared two times sine 60 degree minus 3 times sine 30 degree, which will give us 382 lbf per feet, and direction is upward. Problem 6.29. We have a plate A here, which is 50 centimeter in diameter and has a sharp edge orifice at its center, so the water jet strikes the plate concentrically with a speed of 60 meters per second. So the problem is asking the external forces needed to hold the plate from the orifice with the speed of 60, with the jet has a speed of 60 meters per second. And diameter of the jet is given, and also the diameter of the jet passing through the orifice is also given, which is 0.5 centimeter. So for this problem, because it says the water jet strikes the plate concentrically, which means the water moving in the upward direction here and down direction here is evenly distributed, so we don't have any force in the y direction needed to hold this plate. The only thing we need to consider is the x direction force. So we'll say this is V1, this is V2, and V1 equals to V2 equals to 60 meters per second. And the uppercase diameter D equals to 15 centimeter, which is 0.15 meter, and lowercase d equals to 0.5 centimeter, which is 0.005 meters. Okay, now we're gonna write down the momentum equation in x direction. So x equals to the mass flux moving out times the velocity moving out minus the mass flux moving in times the velocity moving in. So for our case, Fx equals to rho times A1, A2 v2 squared. Because v2 is in x direction, don't have any component in y direction, so v2x actually is the v2 itself. Similarly for v1, which the mass flux calculation is rho times a1 times v1 squared, and x equals to, because v1 equals to v2, rho v squared a2 times a2 minus a1. Okay, so a2 equals to pi over 4 times lowercase d squared minus pi over 4 lowercase d squared. So fx equals to the rho of water, which is 1000 kilogram per cubic meter, times the velocity, which is 60 meter per second. And can take out the pi over 4 as well, leaving only the diameters in the brackets and 0.1, 0.005 meter squared minus 0.15 meter squared. Okay, so our fx will equals to negative 63.6 kilonewton. And because the sign is negative, so it's in the negative x direction, so it's to the left. Now let's look at 6.31. For this problem, we actually have a moving control volume. So the moving speed is 7 meters per second. So the V1 is equals to 20 meters per second, which is the coming in jet. For this kind of problem, we need to use relative velocity to solve for the momentum equation instead of using the absolute velocity, which is 20 meters per second. So the relative velocity, let's say VR, will equals to 20 meters per second minus 7 meters per second, because they are in the same direction. So from the point of the control volume, the V1 coming actually is 13 meters per second. Okay, so we also have here VR coming out at 45 degrees, and we are here coming in, and let's write down the momentum equation in x direction. So we need to keep the signs correct. So because we have only one m dot, so I'm gonna use m dot here. M dot times the moving out mass flux is negative VR times cosine 45 degree, and we have the VR coming in, which is minus dot VR. So therefore we will have fx equals to negative m dot VR cosine 45 degree plus 1. Okay, so now we need to find the m dot. So the m dot equals to rho A V, which is for water 100 kilogram per cubic meter times the area, which we are given the water jet is 6 centimeter in diameter. So it's pi over 4 times 0.06 meter power of 2 times the velocity, which is 13 meter per second. So the m dot is actually 36.76 kilogram per cubic meter. Okay, so we can plug the numbers in. Negative 36.76 kilogram per cubic meter times the velocity, which is centimeter per second, times cosine 45 degree plus 1. So the fx is equals to negative 816. Direction is to the negative x direction. And similarly, we can do the momentum in y direction. And for this case, we will not have any water coming in. So the second term is 0, and we'll have m dot times BR times sine 45 degree, which is 36.76 kilogram per cubic meter times velocity times sine 45 degree. So this will give us 338 Newton, and direction is upward. Now let's look at 6.56. We have a pipe that has a 180 degree bend, and we have the diameter, which is 20 centimeter, and the rho of the water is given, and the Q is given as well, and we have the pressure at inlet and outlet of the pipe, which is P1 and P2. Both are 100 kilopascal here. So the bent volume is given and the bent weight is given. Then we are asking to find the force applied to hold the bent in place. So we have the control volume here as shown. So we have the pressure acting on it. We have the force F Z direction and Fx. Because this one has the weight, we need to consider therefore the vertical direction is Z direction. So the Q here is 0.35 cubic meter per second. The volume of the bend is 0.1 cubic meter, and the weight of the bend itself is 400 Newton. Okay, so first we're gonna find velocity, V, which will equals to Q over A, which is gonna be 0.35 cubic meter per second over 4 times 0.2 meter to the power of 2. And this will give us 11.4 meter per second. Okay, so both the velocity coming in and out is 11.14. Now we're gonna find the pressure force P1, which equals to P2, like that, which will be 100,000 Pascal times the area, which is 0.2 meter. This will be 3.19 Newton. So that's the two forces here. Then we're gonna use the momentum equation in the x direction. So Fx equals to the mass flux difference. Okay, so the sum of forces including both the Fx and the pressure, so 2 times P1 plus Fx equals to the velocity moving out, which is m dot times velocity, and it's in the negative x direction, the minus moving, which is in positive x direction. Okay. So, and the mass m dot is equals to rho AV, which is 1,000 kilogram cubic meter times area, which is 4 times 0.2 meter times the velocity, which is 11.14 meter per second, which will give us 700 Newton So Fx equals to 2 m dot times the V minus 2 P1. So Fx will be negative 2, so the unit should be kilosecond, 100 Newton per second times the velocity, 14 meter per second. Minus 2 times 6,283.19 Newton. Okay, so our final Fx could be negative 14.1 kilonewton. And the direction is to the left. And for the for the mass flow in the z direction, actually we can use the same expression, but we don't have any mass flowing in and out in the control volume. The only thing we need to hold is the weight and weight of the water and weight of the bed. So in that case, Fz equals to the weight of the bed and weight of water equals to 400 Newton plus 0.1 cubic meter times specific weight. So Fz gonna be 1.38 kilonewton and direction is upward. For 6.71, we have a T-shape pipe. We have Q1, Q2, Q3. So Q1 equals to 40 cubic meter per second. Q2 equals to 30 cubic meter per second. And we have P1, which is 100 kilopascal. And P3, 80 kilopascal. And we have P2, which is 70 kilopascal. So for this case, we for the control volume, we have a V1, V2, V3 come in and out from the control volume, and we have 3 different pressure force acting on this control volume as well. So for this problem, first we're gonna do is find the Q3. Because of the continuity equation, Q3 will equals to Q1 minus Q2, which is 10 cubic meter per second. And with the Q, we can find the velocity V1, V2, V3. So V1 equals to Q1 over A1, which is gonna be Q1 is given, and A1 we have the diameter of 0.1, so can use pi over 4 times the diameter, which is 0.15 meter to the power of 2. Therefore, we can get the value, which is 22.63 meter per second. Similarly, we can find V2, which is Q2 over A2. Q2 is 30 meter per second. Divided by pi over 4 times diameter here, which is 0.07. Which our final answer will be 77.95 meter per second. And for V3, it's the similar thing, Q3 over A3. That will be 10 cubic meter per second, pi over 4 times diameter, which is 0.15. Which gives us 5.659 meter per second. Then we can use the momentum equation in the x direction. Sum of the force equals to the mass flux change. So the force including the Fx and the pressure. So for P1 is acting on the positive x direction, and P3 is negative x direction. So plus P1 A1 minus P3 A3 equals to M3 V3 minus M1 V1. Okay. So now we can plug the numbers in. Fx plus the pressure is 100 kilopascal and 80 kilopascal. Yeah. Which is 0.15 plus, minus which equals to the mass flux which is rho AV because M3 is in the positive x direction, so it's positive, and which is same for the M1 here. Times the velocity. So our fx is gonna be negative 8,840 Newton to the x direction. And then we're gonna do the momentum equation in y direction. Fy equals to so Fy, here we only have the 0.3 values, which will be Fy plus P3A3 equals to, because we have nothing to move out, so it's 0 for the first term, it will be negative so A3 B3. Like that. Okay. So Fy equals to negative rho A3 B3y, which is the V3. So V2. Minus P2A2. Kilogram per cubic meter times the area, which is 4 times 0.07 meters. And the velocity is 77.95. The pressure is negative, 70,000 kilopascal times area. 0 meter, and Fy is equals to negative 23700 Newton. So the direction is downward. Let's look at last problem 6.75. So we have a propeller on a boat, and we have a stream 3 feet a diameter with the velocity equals to 100 feet per second. So the first part of the problem is asking what of the force it can produce when the boat is stationary. And second question is asking what is the force when the boat is moving at 30 feet per second. So let's first do the part one. We have a velocity coming out, and from the problem statement we will assume we don't have any mass flux flowing to the control volume. So for this case, we can find our mass flux equals to rho AV, which is gonna be, so the rho, because we given the temperature, we can find in the appendix. Feet times the power 3 feet, this is the area, times the velocity, which is 100 feet per second. So our mass flux is going to be 1.612 per second. Okay, so now we can use the momentum equation in x direction. So the sum of the forces equals to the sum of the mass flowing out, mass flux times velocity flowing in. Okay, so only have one force, which is Fx, and because we don't have anything flowing in, we only have m dot times the velocity, and it's in the positive x direction. Okay, so Fx equals to 1.612 per second times the velocity, which is 100 feet per second. Which gives you 161 pound force. Okay, so that's your propulsive force. And for part two, we will have a velocity moving, which is gonna be 30 feet per second. Therefore, I'm gonna use VR here, which is gonna be 100 feet per second minus 30 feet per second, which gives you 70 feet per second. Then we're gonna use same thing for the momentum equation. X equals to m dot times the v r, which the direction is positive, so be 1.612 slot per second times 70 feet per second, which will gives you 113 pound force.